The electricity coming out of batteries is direct current, DC. The electricity flows directly from negative to positive. Let's move upscale a little bit. What is the voltage coming out of a wall socket? And by that I mean North American wall sockets. Now, some of you may know already. It's 120 volts, but this is alternating current, or AC. Direct current flows from negative to positive, but alternating current actually reverses polarity 60 times per second here in North America. In other words, if we were able to measure the voltage on these two connections, the third connection is a ground connection, and it literally is hooked up to ground. I'll explain that a little later in this video series, but it's not important right now. It's these other two prongs that are the business end of the electrical outlet. If we were to measure the electricity on these plugs, the right one would be plus 60 volts. The left one would be minus 60 volts. Measuring from one pole to the other is 120 volts, with the electrons coming out of the left pin and flowing into the right-hand pin. In 1/60th of a second, the voltage on each pin will drop to 0, and then reverse with positive 60 volts on the left pin and negative 60 volts on the right pin. In 1/60th of a second later, it changes again. Electrons would flow out of the right pin, because it's negative, and go into the left. 1/60th of a second later, it changes again. It reverses polarity 60 times per second. We'll get into why it does this and the practical reasons they make that kind of electricity, but I want to emphasize the difference between AC and DC current. Now, the wall outlet here in North America is 120 volts. Now, this is a high enough voltage to kill, though usually it is just really, really unpleasant getting such a shock. However, your brain sends signals to your muscles electrically. In other words, to close your hand, the brain sends electrical signals to your muscles, down your nerves, which react by tensing up. So you'll notice if you get a shock, your muscles respond by pulling or tensing themselves. This is dangerous because, say, if you were to grab a wire, a live electrical wire, the electricity triggers the muscles in your hand to tense up, effectively giving your hand muscles a false signal instead of your brain. Your hand will then grip that wire with an impossibly strong grip, and you can't let go. 120 volts is a far higher voltage than your brain is putting out. Sadly, you are now electrocuting yourself to death, as the electricity flowing through your body is both burning you and causing other muscles to misbehave. Important muscles like, your heart, your diaphragm, which is what makes you breathe, etc. So, one quick safety tip. If you're working on wires, let's say you're fixing an electrical outlet, you turn off the breaker. Before you go grabbing that wire, maybe you made a mistake. You turned off the wrong breaker and the wire is still live. Don't grab the wire. Instead, touch it first with the back of your hand. If it's still live, then your muscles in your hand and arm will tense up. You'll make a clenched fist, the muscles in your arm will tense up, and you will punch yourself in the nose, and this will be an excellent reminder to never ever do that again. Now, let's move up another level of voltage. In Europe, The electrical outlets are 240 volts AC. And in your North American home as well, you will find it in places like your hot water tank, your oven, water pumps, and your clothes dryer. Now we're getting into the most dangerous voltages, which are typically between 200 and 600 volts. If you get hit with a voltage higher than 600 volts, your muscles tend to tense up so violently that it throws you off of the electrical source. 200 volts and up is a very, very dangerous voltage that can kill you real quick, stopping your heart, sending your diaphragm into spasms, all kinds of nasty stuff. You also will tend to hold on to wires instead of being thrown off. So this is a very dangerous voltage range. So let's move up the voltage even more. The transmission lines that run down your street are typically in the thousands of volts. These wires don't just have a very high voltage, but they also have an incredibly high current. 7,200 volts is enough electrical pressure that it can turn insulators into conductors. Any material will conduct electricity if enough voltage is applied to it. So things like the string on your kite or a tree branch. And obviously such voltages are very likely to kill you, but at the very least burn you really badly. Contact with such high voltages can cause your muscles to tense up so strongly and violently that you can literally break your own bones. This is why electrical injuries can often be accompanied by burns, heart failure, and broken bones. So let's move up even more. Long-distance transmission lines typically operate in the hundreds of thousands of volts to over 1,000,000 volts. Now remember I said anything will conduct electricity if enough voltage is supplied. This includes air. Such voltages are now sufficiently high enough that you no longer need to even touch the wire to get a shock. If you even come close to the wire, the electricity will reach out and touch you. And it won't be a pleasant touch. Transformer stations convert this really high voltage electricity, and sadly, more than one kid has climbed the fences to go into these substations and wound up getting killed. They probably thought that, as long as they didn't touch the wires, they'd be safe. And so they were playing in the danger zone. And you know what? They probably didn't touch the wires. The voltage was high enough to just jump through the air and electrocute them when they got close to the wires. You see these huge glass insulators? If you look at their cross section, you can actually see that they have been designed to maximize the path the electricity needs to take. Some of these electrical insulators can be over 10 feet long, and each glass insulator is specifically designed so the electricity has to go a really long way to get across the insulator. Say it's wet out because it's raining. The farther apart these two wires are, the farther the air gap is that the electricity has to travel, the greater the resistance. So the insulators are specifically designed to make the distance the electricity has to travel really high. All of these electrical systems generate and transmit AC, or alternating current. The electricity actually reverses direction dozens of times per second. In North America, it's typically 60 hertz or 60 times per second. In Europe and some places in South America, it's 50 hertz or 50 times per second.